For decades, Saturn's largest moon was nothing more than an orange blur, a hazy ball of mystery hanging in the darkness of the outer solar system. Scientists could only guess what lay beneath that thick, suffocating atmosphere. They built theories, they made predictions, and then we finally sent spacecraft to see for ourselves. What they found was not what anyone expected. The real images of Titan show that something is deeply, fundamentally off about this world. If you find this journey through the cosmos relaxing, please take a moment to like this video and subscribe to Cosmic Drift. Your support helps us continue exploring the strangest corners of our universe together. Let us begin with what makes these images so unsettling. You would expect a moon this far from the sun to be a dead, frozen wasteland. You would expect craters everywhere, like our own moon or the moons of Jupiter. You would expect silence, stillness, a world that gave up on change billions of years ago. But Titan refuses to follow the rules. The images we have captured reveal a world that is alive in ways we never imagined. Not alive with creatures, at least not that we know of, but alive with movement, with weather, with rivers and lakes and seas, with towering dunes that stretch for hundreds of miles, with mountains that rise into orange skies, with islands that appear out of nowhere and then vanish without a trace. This is the story of what we found when we finally pulled back the veil on Titan, and why those images continue to puzzle scientists to this day. Our journey begins with the barrier that kept Titan hidden from us for so long. That thick golden atmosphere. When the Voyager spacecraft flew past Saturn in the early 1980s, they turned their cameras toward Titan with great anticipation. Here was a moon larger than the planet Mercury. Here was a world with an atmosphere denser than Earth's. Surely the cameras would reveal something spectacular. Instead, they saw nothing but orange haze, a smooth, featureless ball of smog that blocked every attempt to see the surface below. It was like trying to peer through a window caked with mud. The images came back showing only that golden color, that uniform veil of mystery. Scientists were disappointed but also intrigued. What could possibly be hiding beneath all that haze? The atmosphere itself was the first strange discovery. It is made mostly of nitrogen, just like the air you are breathing right now. About 94% nitrogen, with most of the rest being methane. This sounds simple enough until you realize what this means. Titan has an atmosphere that is actually denser than Earth's. The pressure at the surface is about 50% higher than what you feel standing at sea level on our planet. If you could stand on Titan, you would feel that extra weight pressing down on you. The air would be thick around you, heavy and cold. But it is not the nitrogen that creates that orange color. It is something far more interesting. High in Titan's atmosphere, ultraviolet light from the distant sun breaks apart methane molecules. The pieces recombine into heavier, more complex organic compounds. These are called tholins. They are sticky, tar-like particles that slowly drift downward through the atmosphere like an endless rain of organic snow. Over billions of years, this material has accumulated on the surface in quantities that scientists can barely comprehend. The haze is so thick that visible light cannot penetrate it. Standing on the surface of Titan, you would find yourself in a dim, orange world. The sunlight would be about 100 times weaker than what we experience on Earth. Imagine the darkest, haziest day you have ever experienced. A day when wildfire smoke fills the sky and everything takes on that eerie orange tint. Now imagine that every single day, forever. That is Titan. This haze frustrated scientists for years. Every telescope pointed at Titan saw the same thing. That orange blur, that golden mystery, the surface remained hidden, and theories about what lay beneath grew wilder and wilder. Some scientists predicted a global ocean of liquid methane. Others imagined vast tar pits or endless plains of organic sludge. Without being able to see through the haze, there was no way to know for certain. Everything changed in 2004 when a spacecraft named Cassini arrived at Saturn. This was no simple flyby mission. Cassini was designed to orbit Saturn for years, studying the planet and its many moons in unprecedented detail. But the real prize, the object of intense scientific curiosity, was always Titan. And Cassini came equipped with tools that could finally pierce that orange veil. The key was radar. While visible light bounces off the haze particles and scatters uselessly, radar waves pass right through. Cassini could beam radar signals down through the atmosphere and map the surface below with remarkable clarity. For the first time in history, we could see what Titan had been hiding all along. The images that came back were shocking. Instead of a featureless plain of ice and organic gunk, Cassini revealed a world that looked hauntingly familiar. There were mountains and valleys. There were river channels carved into the surface. There were vast dark regions near the poles that looked suspiciously like bodies of liquid. There were enormous fields of dunes stretching across the equator. This was not a dead world. This was a world with active geology, active weather, and landscapes that echoed our own Earth in the strangest ways. But Cassini was not alone in its mission to Titan. Attached to the spacecraft was a small probe built by the European Space Agency. It was named Huygens, after the Dutch astronomer who discovered Titan in 1655. On Christmas Day 2004, Huygens separated from Cassini and began its journey toward the moon. 20 days later, it would do something no human-made object had ever accomplished before. It would land on a moon in the outer solar system. The descent of Huygens through Titan's atmosphere lasted about 2.5 hours. As the probe fell through the haze, its instruments measured everything they could: temperature, pressure, wind speed, chemical composition, and its cameras pointed downward, capturing images of the approaching surface. What those cameras saw changed everything we thought we knew about Titan. As Huygens descended below 40 kilometers altitude, the haze finally began to thin. The cameras could make out surface features below, and what they revealed was a landscape that could have been plucked straight from Earth. There were channels carved into brighter highlands. These channels flowed downward into darker, flatter lowlands. They branched and merged exactly like river systems on our planet. The patterns were unmistakable. Something had flowed across this surface. Something had eroded these channels over time. Something liquid had shaped this world. The landing itself was gentle. Huygens touched down at a speed similar to dropping a ball from about 1 meter high. It made a small dent in the surface, bounced once, and slid a short distance before coming to rest. The surface had the consistency of damp sand or wet snow, and scattered across that surface were pebbles, rounded, smooth pebbles made of water ice. They range from a few centimeters to about 15 centimeters across. Their edges had been worn down, their surfaces smoothed by some process of erosion. On Earth you find pebbles like this in riverbeds. The flowing water tumbles them against each other, grinding away the sharp edges over time. The fact that Titan's pebbles looked so similar suggested the same process at work here. But the liquid that shaped them was not water. It was something far more exotic. Huygens transmitted images from the surface for about 72 minutes before Cassini moved beyond the horizon, and communication was lost In those precious minutes, the probe captured images of its final resting place. A flat plain covered in those rounded pebbles, a dark surface that appeared to be wet. Scientists would later determine that Huygens had landed in what appeared to be a dry riverbed, a place where liquid had flowed in the past, leaving behind these telltale signs of erosion. But here is where things start to get truly strange. The liquid that carved these channels, that rounded these pebbles, that filled the lakes and seas we would later discover, is not water. At temperatures hovering around -179 degrees Celsius, water on Titan is frozen as hard as rock. The water ice forms the bedrock of this world. It makes up the pebbles and the mountains and the frozen ground beneath your feet. No, the liquid on Titan is something else entirely. It is methane, the same gas that burns in your stove, the same compound that sometimes bubbles up from swamps on Earth. On Titan, where temperatures are so incredibly cold, methane can exist as a liquid. It rains from the sky. It flows down rivers. It collects in lakes and seas. Titan has a complete weather cycle, just like Earth. But instead of water, it runs on hydrocarbons. This discovery was profound. Titan became only the second world in our entire solar system known to have stable bodies of liquid on its surface. The first, of course, is Earth. Everywhere else is either too hot, where liquids would evaporate instantly, or lacks the right atmospheric conditions to keep liquids stable. But Titan, cold and strange as it is, has found a way to maintain liquid on its surface for what may be billions of years. The images from Cassini's radar revealed the full extent of this liquid world. Near the North Pole, 3 enormous seas dominate the landscape. The largest is called Kraken Mare, named after the legendary sea monster of Norse mythology. It covers an area roughly the size of the Caspian Sea on Earth. Some estimates suggest it may be even larger than all 5 Great Lakes combined. Radar soundings indicate that the deepest parts of Kraken Mare may exceed 300 meters. That is deep enough to swallow some of Earth's most impressive skyscrapers. Next in size is Ligeia Mare, named after one of the sirens from Greek mythology. This sea is about 50% larger than Lake Superior. Radar measurements have probed its depths and found it to be surprisingly pure. The liquid is almost entirely methane, with very little ethane mixed in. This was unexpected. Scientists had predicted that ethane, which is heavier and produced constantly in the atmosphere, would accumulate in the seas. The fact that Ligeia Mare is mostly methane suggests something is removing or transforming the ethane. Perhaps it is seeping into the ground. Perhaps it flows into Kraken Mare. The mystery remains unsolved. The third major sea is Punga Mare, smaller than the others but still substantial. Around these seas cluster dozens of smaller lakes. Some are comparable to large lakes on Earth. Others are small ponds, barely visible in the radar images. The northern polar region of Titan is dotted with these liquid bodies, creating a landscape that would not look entirely out of place in Finland or northern Canada. Except, of course, the lakes are filled with liquid natural gas, and the temperature is cold enough to freeze you solid in seconds. The southern hemisphere tells a different story. Despite similar terrain, the south has only one confirmed lake, called Ontario Lacus. This asymmetry puzzled scientists, until they realized they might be seeing the effect of seasons. Saturn takes about 30 years to orbit the Sun. Titan, being a moon of Saturn, experiences these same long seasons. When Cassini arrived, it was late southern summer on Titan. The south may have dried out as methane evaporated into the atmosphere. Meanwhile, The North was in winter, and its seas were full. Perhaps in 15 years the situation will reverse. But the lakes and seas were not the strangest thing the images revealed. That honor goes to features that scientists came to call the Magic Islands. In 2013, as Cassini was imaging Ligea Mare, something impossible appeared in the data. A bright spot showed up in the sea where nothing had been before. It looked like an island, but when scientists checked earlier images of the same location, there was nothing there. And when they looked again later, the island had vanished. It simply ceased to exist. This was not a glitch or an error in the data. The feature was real. It appeared in multiple radar passes. Scientists calculated its size at roughly 30 square miles, about the area of Manhattan. Then it was gone. Then, in 2014, it came back, but this time it was bigger, nearly twice the size it had been before, and then it vanished again. These magic islands have now been spotted in several locations across Titan's seas. They appear, they change size, they disappear. No one knows for certain what they are. Several theories have been proposed. Perhaps they are waves, catching the radar in just the right way to create a false signal. But the waves on Titan's seas are incredibly small, just millimeters high. It seems unlikely they could create such strong radar returns. Perhaps they are bubbles of nitrogen gas rising from the depths. The seas contain dissolved nitrogen, and changes in temperature or pressure could cause it to fizz out of solution, creating streams of bubbles that rise to the surface. This could explain why the islands appear and disappear, but it struggles to explain why they would persist for weeks at a time. The most intriguing theory involves floating solids. Remember that constant rain of organic particles falling from Titan's atmosphere. These tholins accumulate on the surface over time. Some researchers believe they could form porous, sponge-like structures. If these structures are porous enough, perhaps containing 25 to 60% empty space, they might be able to float on the methane seas. They would drift like icebergs, accumulating near the shores and occasionally breaking off to float across the surface. Over time, liquid methane would seep into the pores, eventually causing them to sink and disappear from view. This explanation is elegant because it ties together several observations. The shores of the seas do appear to be saturated with hydrocarbons. The organic rain is constant and has been falling for billions of years, and the timing matches. The magic islands appear for days or weeks before vanishing, consistent with the time it would take for liquid to infiltrate a porous solid. But nothing is certain. The magic islands remain one of Titan's most enduring mysteries. They represent something we rarely see in planetary science: active, ongoing change on a world beyond Earth. Whatever these features are, they tell us that Titan's seas are not static pools of liquid. Something is happening out there, something we do not fully understand. If the seas of Titan represent one extreme of this strange world, the equatorial regions represent another entirely. Here, far from the liquid methane of the poles, stretch vast fields of dunes. These are not small ripples in the sand. These are massive structures, some of them hundreds of kilometers long, rising to heights of 100 meters or more. They are among the largest dunes in the entire solar system. The images show them clearly. Dark streaks running east to west across the equatorial regions, covering about 13% of Titan's surface. That is an area roughly equivalent to Canada. All of it dominated by these enormous linear dunes. They look remarkably similar to dunes found in the Namib Desert of Africa or the Arabian Peninsula on Earth. long, parallel ridges of sand shaped by prevailing winds into repeating patterns. But what are these dunes made of? Not silicate sand like on Earth. The composition is organic. The same complex hydrocarbon compounds that rain down from the atmosphere have accumulated here in quantities almost beyond imagination. Over billions of years, this organic material has been processed by wind, by possible liquid flows, and by unknown chemical reactions into particles roughly the size of sand grains. Scientists describe these grains as similar in size and texture to coffee grounds. The exact chemistry is still being worked out. Studies suggest the dune material contains polycyclic aromatic hydrocarbons, compounds related to naphthalene and other chemicals. These are the same types of molecules found in car exhaust and industrial pollution on Earth. On Titan, they form naturally through the action of sunlight on methane. They represent some of the most complex organic chemistry happening anywhere in our solar system outside of Earth. Experiments on Earth have demonstrated how this might work. Researchers exposed acetylene ice to conditions simulating cosmic ray bombardment. The results were striking. Simple molecules transformed into complex organic compounds, including the aromatic hydrocarbons that seem to make up Titan's dunes. This suggests that the dune material is not just falling from the sky. It may also be forming through chemical reactions on the surface itself. There is another strange property of Titan sand. It appears to be electrically charged. On Earth, our stronger gravity overwhelms any static electricity in sand grains. But Titan's gravity is much weaker, about 1/7 of Earth's. And its atmosphere is different too. It is denser, drier in the sense that it lacks water vapor, and filled with electrically insulating organic particles. Under these conditions, sand grains can build up significant static charges as they tumble against each other in the wind. This electric sand may help explain one of the puzzles about Titan's dunes. The prevailing winds on Titan blow from east to west, yet the dunes appear to form from west to east, in the opposite direction. How can this be? One possibility is that the static charge makes the sand stickier than expected. The sand clings to itself and to the surface. Only the strongest winds can move it. And those strong winds might blow in the opposite direction from the gentle prevailing breezes. Standing among those dunes, if you could somehow survive the conditions, would be a surreal experience. Imagine towering hills of dark organic material rising around you. The sky above would be a dim orange, the sun barely visible through the eternal haze. The air would be thick and cold, pressing against you with a weight greater than Earth's atmosphere. And beneath your feet would be sand made of the same complex organic molecules that form the basis of life on our own world. The dunes occupy the equatorial regions because those areas are drier. The methane rains fall more heavily near the poles, keeping those regions moist and preventing dune formation. But near the equator, the climate is more arid. The organic particles can accumulate, dry out, and be shaped by the wind into these massive structures. It is a delicate balance of weather and geography that creates distinct climate zones on this distant moon. Between the seas of the north and the dunes of the equator lie regions of plains and mountains. The plains are vast, smooth, expanses that cover much of Titan's surface. Their exact nature is uncertain. They may be deposits of organic sediment, blown in from the dune fields or washed down from the highlands. Or they may be frozen deposits from ancient seas that once covered wider areas. The radar images show them as relatively featureless expanses, neither as dark as the dunes, nor as bright as the icy highlands. The mountains of Titan are modest by Earth standards. The tallest known range rises to about 3 kilometers above the surrounding terrain. This may not sound like much compared to the Himalayas, but for a moon made largely of ice, it is substantial. Scientists believe these mountains are composed primarily of water ice, with coatings of organic material giving them their characteristic appearance in radar images. The mountains show signs of tectonic activity. There are ridges and valleys, faults and folds. Something is deforming Titan's crust from below. This hints at what may be one of Titan's most important secrets. Beneath that icy surface, hidden from direct observation, may lie an ocean of liquid water. The evidence comes from multiple sources. Cassini measured how Titan's shape changes as it orbits Saturn. Because Titan's orbit is slightly elliptical, it moves closer to and farther from Saturn over the course of each orbit. Saturn's gravity pulls on Titan, creating tides not in liquid on the surface, but in the solid body of the Moon itself. These are called solid body tides. If Titan were completely solid all the way through, these tides would cause the surface to flex by only about 1 meter. But Cassini measured tidal flexing of about 10 meters. That is 10 times more than expected. The only way to explain this is if something inside Titan is not solid. There must be a liquid layer beneath the ice shell that allows the surface to flex more freely. Additional evidence came from the Huygens probe. As it descended through the atmosphere, it detected extremely low-frequency radio waves. The Titan's surface is not a good reflector of these waves, so they must have been reflecting off something else. That something else appears to be a layer of liquid water beneath the ice, perhaps 35 to 80 kilometers below the surface. This interior ocean is not liquid methane. It is liquid water, possibly mixed with ammonia. The ammonia acts as antifreeze, allowing the water to remain liquid at temperatures that would otherwise freeze it solid. Scientists estimate the ocean may be hundreds of kilometers deep, containing more liquid water than all the oceans on Earth combined. The implications of this hidden ocean are staggering. Titan may harbor 2 separate environments where life could potentially exist. On the surface, there are the methane seas and the organic chemistry raining down from above. Beneath the ice, there is a vast ocean of liquid water, the universal solvent that enables life as we know it. Titan could be a world with not 1 but 2 potential habitats for living things. But life on Titan, if it exists, would be unlike anything we know. Consider the surface conditions. The temperature hovers around minus 179 degrees Celsius. At these temperatures, any biochemistry based on liquid water would simply freeze solid. Water molecules cannot move, cannot interact, cannot enable the complex chemical reactions that life requires. Any living thing on Titan's surface would need to use a completely different solvent. This is where the methane becomes interesting. Liquid methane could theoretically serve as a solvent for life, but it behaves very differently from water. It has a much lower surface tension, meaning it does not cling to molecules as well as water does. It has different solubility properties, dissolving different types of compounds. Any life that used liquid methane as its medium would need a completely different biochemistry than anything on Earth. In 2005, astrobiologist Chris McKay proposed what such life might look like. Instead of breathing oxygen like we do, Titanian organisms might breathe hydrogen. Instead of eating sugars, they might consume acetylene, one of the organic compounds produced in Titan's atmosphere. And instead of exhaling carbon dioxide, they would exhale methane. These organisms would essentially run on a chemistry that is the reverse of photosynthesis on Earth. This theory led to a prediction. If such organisms existed in large numbers, they would be consuming hydrogen from the atmosphere near the surface. They would also be consuming acetylene, one of the most energy-rich compounds on Titan. Scientists could potentially detect their presence by looking for these chemical signatures. A depletion of hydrogen near the surface, a shortage of acetylene. If both conditions were met, it would be consistent with the presence of methanogenic life. In 2010, scientists analyzing Cassini data made a startling announcement. They had found exactly those signatures. The hydrogen puzzle came first. Models of Titan's atmosphere predicted that hydrogen, produced high above by ultraviolet light, breaking apart methane, should be distributed fairly evenly throughout the atmosphere. Some would escape to space. The rest should mix throughout the atmospheric layers. But that is not what Cassini found. Instead, hydrogen appeared to be flowing downward through the atmosphere and disappearing at the surface. The rate was enormous. About 10,000 trillion hydrogen molecules per second were vanishing at ground level. Something was removing hydrogen from the atmosphere faster than it could be replenished. As one scientist put it, it was like spraying hydrogen onto the ground with a hose and watching it vanish. The acetylene mystery was equally strange. This compound is produced in abundance in Titan's upper atmosphere. It should rain down onto the surface and accumulate over time. Models predicted significant deposits of acetylene on the surface. But when scientists mapped the surface composition, they found almost none. The acetylene was simply not there. Something was removing it, consuming it, transforming it into something else. These two findings together sent a ripple of excitement through the astrobiology community. Here were exactly the signatures that McKay had predicted for methanogenic life. Hydrogen disappearing at the surface, acetylene being consumed. It matched the theory perfectly. But scientists are cautious by nature, especially when the implications are so profound. There could be non-biological explanations for these observations. Perhaps some mineral on Titan's surface acts as a catalyst, combining hydrogen and acetylene through purely chemical reactions. Perhaps sunlight or cosmic rays are transforming the acetylene into more complex compounds that we cannot detect. The absence of a substance is difficult to interpret. It tells you that something is happening, but not necessarily what. To date, we cannot say whether life exists on Titan. The evidence is tantalizing but inconclusive. What we can say is that Titan has the ingredients and conditions that might allow life to exist. It has liquid solvents on the surface. It has an atmosphere rich in organic compounds. It has energy sources in the form of chemical gradients. And it may have a subsurface ocean of liquid water. If life can arise under any of these conditions, Titan would be a prime candidate. The possibility of life brings us to one of the strangest aspects of Titan's images: the lack of impact craters. Every solid body in the solar system is scarred by billions of years of cosmic bombardment. The Moon is covered in craters. Mercury is covered in craters. Mars, the moons of Jupiter, the moons of Uranus and Neptune, all bear the marks of ancient impacts. Even Earth would be covered in craters if not for erosion and tectonic activity that constantly resurface our planet. Craters are the default state of solar system bodies, but Titan has remarkably few. When Cassini began mapping the surface with radar, scientists expected to find thousands of impact craters. Titan is a large target, and it has been orbiting Saturn for billions of years. It should have accumulated countless scars from asteroid and comet impacts. Instead, Cassini found only a handful of definite craters and perhaps a few dozen possible ones. The surface was almost suspiciously smooth. This tells us something profound about Titan. Its surface is young, not young in human terms, but young in geological terms. The features we see today have not been there since the formation of the solar system. Something has been erasing the craters, resurfacing the moon, wiping the slate clean over and over again. Several processes could be responsible. The thick atmosphere provides some protection. Smaller impactors burn up before reaching the surface, just as they do on Earth. But this cannot explain the lack of large craters. The atmosphere cannot stop kilometer-sized objects. Erosion is almost certainly playing a role. The methane rain, the flowing rivers, the wind that shapes the dunes, all these processes wear down and fill in craters over time. On Earth, most ancient craters have been erased by water erosion and plate tectonics. On Titan, similar processes are at work, just using different materials. There may also be geological activity beneath the surface. Cryovolcanism, the eruption of water and ammonia ice from the interior, could be resurfacing parts of Titan. Scientists have identified features that look like volcanic, calderas and flow deposits. If this ice volcanism is active or was active in the recent past, it could be burying craters under layers of fresh material. The implication is that Titan is not a frozen static world. It is a dynamic world, constantly changing, constantly renewing itself. The surface we see today may be only hundreds of millions of years old, a fraction of the solar system's age. This makes Titan fundamentally different from most moons, which preserve their ancient surfaces like fossils in stone. This dynamism is evident everywhere in the images. The river channels show evidence of recent flow. The shores of the lakes appear to fluctuate with the seasons. The dunes are actively being shaped by wind. Even the magic islands demonstrate that change is happening in real time during the brief span of our observations. Consider what this means. On most worlds, what you see is what has always been there, at least since the era of heavy bombardment ended billions of years ago. But on Titan, the landscape is a work in progress. The features we observe now may not be there in a million years. New lakes may form, old dunes may migrate, mountains may rise and erode away. Titan is alive with geological activity in a way that few other moons can match. The images also revealed another strange feature of Titan, a phenomenon that scientists did not expect at all. The surface appears to be shifting. Between 2004 and 2007, Cassini made precise measurements of Titan's rotation. By tracking surface features with radar, scientists could determine exactly how fast the moon was spinning and how that spin was oriented. What they found was bizarre. The surface appeared to be rotating faster than it should. Over the course of those 3 years, surface features had shifted by about 19 miles from where they should have been. This does not mean Titan is spinning up like a top being wound. Instead, it suggests that the surface is not rigidly connected to the interior. The icy crust appears to be floating on something below. That something is almost certainly the subsurface ocean we discussed earlier. The crust slides around on top of this liquid layer, pushed by the pressure of the wind against Titan's mountains. Imagine a giant spherical ship made of ice, floating on a global sea. The wind fills its frozen sails and pushes it slowly across the water. The ship does not go anywhere, of course, because it is completely enclosed, but it rotates slightly, slipping against the liquid beneath it. That is what Titan's surface appears to be doing. This has profound implications for understanding Titan's interior. The crust and the deep interior are essentially decoupled. They can move independently of each other. Energy and material can flow between them in ways that would not be possible if Titan were solid all the way through. Let us return to the atmosphere, because there is another mystery hiding in plain sight. The methane should not be there. When ultraviolet light from the sun strikes methane molecules in the upper atmosphere, it breaks them apart. The fragments recombine into more complex compounds, eventually forming the tholins that rain down onto the surface. This process is one way. Once methane is converted into heavier hydrocarbons, it does not turn back into methane through simple chemical reactions. The atmosphere acts as a methane-destroying machine, constantly consuming this gas and transforming it into something else. Scientists have calculated how quickly this destruction happens. The rate is fast enough that all the methane in Titan's atmosphere should be depleted within about 50 million years. That sounds like a long time, but the solar system is 4.5 billion years old. If methane were produced only once, early in Titan's history, it should have disappeared long ago. The fact that it is still there means something is actively replenishing it. But what? This is one of the great unsolved mysteries of Titan. One possibility is that methane is stored beneath the surface in a form called clathrate. These are cage-like structures of ice that can trap gas, molecules inside them. Methane clathrates exist on Earth, locked in permafrost and beneath the ocean floor. They contain enormous amounts of natural gas. If similar deposits exist beneath Titan's surface, they could slowly release methane over time as the crust shifts and cracks. Another possibility is cryovolcanism. If volcanoes on Titan erupt mixtures of water, ammonia, and methane from the interior, they could be supplying the atmosphere with fresh methane. Several candidate cryovolcanic features have been identified on the surface: dome-shaped structures, flow-like features, and calderas that resemble volcanic craters on Earth. But proving that these features are truly volcanic in origin has been difficult. A more exotic possibility ties back to the question of life. If organisms are consuming hydrogen and acetylene on the surface, they would be producing methane as a waste product. This is exactly what methanogens do on Earth. These microbes live in oxygen-free environments like swamps and digestive systems, producing the methane that bubbles up from bogs and gives natural gas its combustible properties. If titanian methanogens exist in sufficient numbers, they could be the source of the atmospheric methane. This theory is elegant because it explains multiple observations at once. The disappearing hydrogen, the missing acetylene, and the persistent methane could all be products of a global biosphere, invisible to our instruments but shaping the moon's chemistry on a planetary scale. It is a thrilling idea, but it remains unproven. Whatever the source, the methane cycle is real. It drives the weather systems that shape Titan's surface. It fills the lakes and seas. It rains from the clouds and flows down rivers. It evaporates back into the atmosphere to begin the cycle again. This methane cycle is eerily similar to the water cycle on Earth. Both involve a liquid compound that transitions between surface, atmosphere, and underground reservoirs. Both drive erosion and deposition. Both create recognizable landscapes of rivers, lakes, and coastlines. The parallels between Titan and Earth are striking and unsettling. Here is a world 10 times farther from the Sun than our planet. A world where water is frozen as hard as granite and methane flows like water. A world where the sky is orange and the ground is made of organic compounds. Yet the processes at work, the cycles of evaporation and precipitation, the erosion of highlands and filling of basins, these are fundamentally the same as on Earth. The rules of physics and chemistry apply everywhere, creating familiar patterns even in the most alien environments. When you look at images of Titan's river deltas, you could mistake them for aerial photographs of rivers on Earth. The branching patterns, the way tributaries merge into main channels, the spread of sediment where rivers meet bodies of liquid, all of these are instantly recognizable. The same equations that describe river flow on Earth describe river flow on Titan. Only the materials are different. This universality of physical law is both comforting and challenging. It is comforting because it means we can understand other worlds using the knowledge we have gained on Earth. We do not need new physics to explain Titan's rivers. The same principles apply. But it is challenging because it suggests that what we see on Titan might not be unique. The conditions that create rivers and lakes and weather systems might be common throughout the universe. And if the physical conditions can arise elsewhere, perhaps the biological conditions can too. The images of Titan force us to confront a question that has haunted humanity for centuries. Are we alone? Is Earth the only place where complex chemistry has given rise to self-replicating molecules, to metabolism, to evolution, to life? Or is life a common outcome wherever the right conditions come together? Titan does not answer this question directly, but it expands our imagination about what might be possible. Consider the organic chemistry happening in Titan's atmosphere. Sunlight breaks apart simple molecules like methane and nitrogen. The fragments recombine into more complex structures. Those structures combine into even larger molecules. The process continues, building layer upon layer of chemical complexity. The end products include amino acids, the building blocks of proteins on Earth. They include nucleotide, bases, the components of DNA and RNA. These molecules were detected in laboratory experiments that simulated Titan's atmospheric conditions. This is remarkable. Without any liquid water, without any biological activity, Titan's atmosphere spontaneously produces some of the key molecules that life on Earth depends on. The chemistry of Titan is, in some sense, pre-biological chemistry. It creates the raw materials that life could potentially use. Whether that chemistry has actually given rise to life on Titan remains unknown. But the fact that it happens at all suggests that the universe is primed to create complex organic compounds wherever the conditions allow. Laboratory experiments have pushed this even further. When researchers take Tholin material, the organic gunk that rains down on Titan, and expose it to liquid water, something interesting happens. The molecules transform into amino acids and other biologically relevant compounds. On Titan, there is no persistent liquid water on the surface, but there are transient opportunities. When an asteroid impacts the icy crust, the heat can melt water locally for brief periods. That liquid water might mix with the organic material on the surface. For a few thousand years, as the impact melt slowly refreezes, conditions might favor the formation of prebiotic molecules. Then the water freezes again, preserving whatever chemistry has taken place. These impact melt pools are tantalizing targets for future exploration. They represent places where Titan's abundant organic chemistry might have progressed towards something even more complex. They are frozen laboratories, capturing moments when water and organics came together. What happened in those moments? Did chemistry advance towards something like life? The images from Cassini cannot tell us. We would need to go there, to land, to scoop up samples and analyze them. That is a challenge for future missions. The subsurface ocean presents an entirely different possibility. If liquid water exists beneath Titan's ice shell, it has been there for billions of years. Unlike the brief impact melt pools, this is a stable, long-lived environment. It is isolated from the surface, protected from cosmic radiation and ultraviolet light. If it receives any organic material from above, whether through cracks in the ice or through gradual diffusion, it could be a haven for life as we know it. But there is a catch. Scientists believe a layer of high-pressure ice may separate the ocean from the rocky core beneath. On Earth, hydrothermal vents at the ocean floor provide chemical energy and nutrients that support thriving ecosystems even in the absence of sunlight. If Titan's ocean is cut off from the rocky interior, it may lack these energy sources. The ocean could be sterile, a vast body of water with no way to sustain living organisms. However, recent research suggests that the situation may be more complex. Certain conditions of temperature and pressure may allow brines, salty liquids, to percolate through the ice layer. Material from the rocky core could potentially reach the ocean after all. And earlier in Titan's history, when the moon was warmer, the ocean may have been in direct contact with rock. If life emerged during that early epoch, it may have found ways to persist even after the ice layer formed. All of this is speculation built on speculation. We do not know for certain that the subsurface ocean exists, though the evidence is strong. We do not know its composition, its temperature, or its chemistry. We do not know whether any organic material reaches it from the surface. We do not know whether energy sources are available to support metabolism. Each of these questions represents a gap in our knowledge that only future missions can fill. The images from Cassini and Huygens have revealed a world that challenges our assumptions at every turn. But perhaps the most profound challenge is to our sense of Earth's uniqueness. For so long, we have thought of our planet as special, the blue marble, the only place with liquid oceans, the only place with weather and seasons, the only place where complex chemistry has given rise to life. Titan does not overthrow that specialness, but it does put it in context. Earth is not the only world with bodies of liquid on its surface. Titan has them too, just made of different stuff. Earth is not the only world with a dense atmosphere and weather systems. Titan has those as well. Earth is not the only world where complex organic chemistry occurs naturally. Titan's atmosphere is a factory for organic molecules, churning them out constantly. If Earth is special, it is special in degree, not in kind. The processes that make Earth what it is have analogues elsewhere in the cosmos. This realization can be humbling or inspiring depending on your perspective. It means we are not alone in having an interesting world. The universe is filled with interesting worlds. What makes Earth truly unique may be not its physical characteristics, but its biological ones. Life, intelligent life, technological life, these may be Earth's true distinctions, or they may not be. Titan suggests that the ingredients for life are common. Whether life itself is common remains one of the great unanswered questions. Let us delve deeper into some specific images and what they reveal about Titan's character. One of the most striking images from Cassini shows the Xanadu region. This is a large, bright area near Titan's equator, about the size of Australia. When Cassini's radar mapped it in detail, Xanadu turned out to be a complex landscape of hills, valleys, and drainage channels. Dark lineaments crisscross the terrain, which may represent tectonic faults or erosional channels carved by liquid methane. Xanadu is one of the oldest terrains on Titan. Unlike the smooth plains and dune fields nearby, it shows evidence of extensive geological processing. The surface is crinkled and folded, suggesting either tectonic forces from below or erosional forces from above. Some scientists believe Xanadu may be an ancient plateau that has been weathered and dissected over billions of years. Others think it may be an area of ongoing geological activity. The truth may involve both interpretations. The drainage channels in Xanadu are particularly intriguing. They branch and merge in patterns familiar to any geologist who has studied river systems on Earth. The channels run from higher elevations to lower ones, following the pull of gravity. They converge into larger channels as you move downstream. Some of them appear to empty into the dark regions that surround Xanadu, regions that may once have been lakes or seas. This tells us that liquid has flowed across Xanadu's surface for extended periods, not just once, but repeatedly over geological time. The channels are too well developed to have formed from a single rainstorm. They represent the cumulative effect of countless rainfall events, each depositing more sediment, each carving the channels a little deeper. Titan's weather cycle has been operating for a very long time. Another striking set of images comes from the Vid Flumina region. Here, Cassini's radar revealed a network of canyons and river channels that are flooded with liquid methane. These are not dry channels waiting for the next rain. They are filled right now, their dark radar signature indicating the presence of liquid. The canyons are narrow and steep-sided, carved into the surrounding terrain by erosion. Vid Flumina is located near the second largest sea, Ligea Mare. The canyons appear to drain into the sea, forming a river system that connects highland regions to the liquid reservoir below. In some ways, it is reminiscent of fjords on Earth, the steep-sided inlets carved by glaciers that flood with seawater. But on Titan, the carving was done by liquid methane, and the flooding is by the same substance. The existence of flooded canyons tells us that Titan's liquid levels are not static. At some point in the past, the liquid must have been lower for the canyons to form. Then the levels rose, flooding the canyons and creating the features we see today. This could be a seasonal effect, related to the long Saturn year, or it could be a longer-term change in Titan's climate. Without more data points spread over longer time periods, we cannot say for certain. The Huygens landing site provides another window into Titan's character. The probe touched down in a region that radar images had suggested was relatively flat and smooth. What Huygens found was a dry riverbed, covered in rounded pebbles of water ice. The pebbles ranged from a few centimeters to about 15 centimeters across. Their rounded shapes and sorted sizes suggested they had been tumbled and transported by flowing liquid. The largest pebbles at the landing site were about the size of a clenched fist. The smallest were the size of peas. This size sorting is familiar to anyone who has walked along a riverbed on Earth. Different flow speeds carry different size particles. When the flow slows down, the largest particles settle out first. Smaller particles travel farther before they settle. The result is a sorted distribution, with different sizes in different locations. Huygens apparently landed on a floodplain or alluvial deposit, a place where liquid methane had spread out and slowed down, dropping its load of icy sediment. The area was dry when Huygens arrived, but it had clearly been wet in the past. How recently? That is harder to say. The liquid could have flowed through days before the landing or thousands of years before. The pebbles preserve no record of timing. One detail from the Huygens landing was particularly evocative. As the probe sat on the surface, its instruments detected what appeared to be liquid evaporating. The warmth of the probe, tiny as it was in that frigid environment, seemed to be vaporizing methane from the damp ground beneath it. Scientists also observed what they interpreted as a dewdrop falling past the camera's field of view. Titan's surface, at least at the landing site, appeared to be saturated with methane. The ground was damp, like soil after a rain. This dampness has implications for the cycle of materials on Titan. Organic particles rain down from the atmosphere constantly. They accumulate on the surface over time. But if the surface is wet with methane, those organics may dissolve or be carried away by surface liquids. The methane acts as a solvent, redistributing material across the landscape. Some of it may end up in the lakes and seas. Some may be buried beneath newer deposits. The circulation of material on Titan is not just atmospheric, but also involves the surface liquids in complex ways. Let us talk about the shorelines of Titan's seas, because they reveal another layer of strangeness. The coastlines of Kraken Mare, Ligeia Mare, and the smaller lakes show a variety of morphologies. Some shores are crenulated, meaning they have irregular, jagged outlines with many small inlets and headlands. This suggests erosion by waves or chemical dissolution of the coastline. Other shores are subdued, with smoother, gentler profiles. These tend to have more and longer channels feeding into them, suggesting they are depositional environments where sediment is being added. The variety of coastline types tells us that different processes dominate in different areas. Some shores are being eroded, others are being built up. The balance between these processes depends on local conditions, wave energy, sediment supply, and the composition of the shore material. It is exactly what you would expect from a world with active shoreline dynamics. But one aspect of the shorelines is surprising. They appear to be remarkably stable. Over the course of Cassini's observations, the shorelines of the northern seas did not change significantly. This is different from Ontario Lacus in the south, which showed measurable shoreline recession over the observation period. The southern lake was shrinking, evaporating as summer arrived in the southern hemisphere. But the northern seas remained constant. This stability suggests that the northern seas may be in equilibrium with their environment, at least on short timescales. Methane is evaporating from their surfaces, but it is being replenished at roughly the same rate by rainfall and river inflow. The balance holds steady, keeping the shores fixed in place. Whether this equilibrium will persist as Titan's seasons continue to change is an open question. As northern summer approaches, evaporation rates will increase. Will the seas shrink as Ontario Lacus did? Future observations may tell us. The study of Titan's seas has revealed unexpected details about their composition and behavior. Ligeia Mare, despite its vast size, turns out to be remarkably pure. The liquid is almost entirely methane, with little ethane mixed in. This was surprising because atmospheric chemistry produces plenty of ethane. Where is it going? One possibility is that the ethane is denser than methane and sinks to the bottom of the seas. It may be pooling on the sea floor or seeping into the porous substrate below. Another possibility is that ethane-rich liquid is flowing out of Ligeia Mare into the larger Kraken Mare, which may be more ethane-rich as a result. The purity of Ligeia Mare has implications for potential future missions. If we want to send a submarine to explore Titan's seas, we need to know the composition of the liquid. Methane and ethane have different densities and different acoustic properties. A submarine designed for one might not work properly in the other. The fact that Ligeia Mare is mostly methane simplifies the design problem, at least for that particular body of liquid. Radar soundings have also revealed what lies beneath the seas. Ligeia Mare has depths exceeding 160 meters in places. The radar signal penetrated through the liquid and bounced off the sea floor, allowing scientists to map the basin below. What they found was a floor covered in sludge. The organic particles that rain down from the atmosphere and wash in from rivers have accumulated on the bottom, forming a layer of organic sediment. This sludge is intriguing from an astrobiological perspective. If any biochemistry is happening on Titan, whether full-blown life or just prebiotic chemistry, the seafloor sediments might be a good place to look. Complex organic molecules might accumulate there over time. Chemical reactions might occur in the interface between liquid and sediment. A future probe that could reach the seafloor and sample these sediments might find fascinating organic chemistry. The temperature of the seas provides another piece of the puzzle. Cassini's instruments measured the thermal emission from Ligea Mare and its surroundings. On Earth, you would expect land to warm faster than water as summer approaches. Beaches get hot while the ocean stays cool. But on Titan, the measurements showed no significant difference between the temperature of the sea and the temperature of the nearby shore. Both were warming at roughly the same rate. This suggests that the shoreline terrain is saturated with liquid hydrocarbons. The methane that fills the seas also permeates the ground around them, affecting its thermal properties. The distinction between land and sea is blurred. The shores are not truly dry, but are instead a transition zone where liquid and solid intermingle. This is consistent with what Huygens found at his landing site, even though that site was far from any large body of liquid. Titan's surface, across wide areas, appears to be damp with methane. The clouds of Titan provide yet another window into its atmospheric dynamics. Unlike the constant haze that blankets the moon, clouds are transient features that form and dissipate with the weather. Cassini observed clouds throughout its mission, tracking their movements and trying to understand the conditions that create them. The largest clouds tend to form near the poles, particularly around the South Pole during southern summer. These are methane clouds, analogous to water clouds on Earth. They form when methane vapor rises, cools, and condenses into droplets. The droplets grow until they are heavy enough to fall as rain. This methane rain feeds the lakes and rivers, completing the hydrological cycle. But the cloud patterns on Titan have been puzzling. Scientists expected to see abundant cloud activity over the northern seas during northern summer. As the liquid evaporated and the vapor rose to form clouds. Instead, the northern hemisphere remained relatively cloud-free throughout much of the Cassini mission. Only sparse, small clouds appeared, far fewer than models predicted. This discrepancy suggests that our understanding of Titan's atmospheric circulation is incomplete. There may be factors suppressing cloud formation that we have not accounted for. Perhaps the atmosphere is more stable than expected, inhibiting the vertical motion needed to form clouds. Perhaps the circulation patterns are different from what models predict. Or perhaps the timing is off, and clouds will become more abundant in the future as the seasons progress further. Storms on Titan are expected to be dramatic events. Simulations suggest that cyclones could form over the large northern seas during peak summer, driven by the evaporation of methane and the release of latent heat. These cyclones could generate winds of up to 70 kilometers per hour and torrential methane rainfall. They could persist for days, moving slowly across the sea surface before dissipating. But no such storms were observed during the Cassini mission. The weather remained surprisingly calm, at least from what we could see. This could mean the storms are less frequent or less powerful than expected. Or it could mean they happened during periods when we were not observing. or it could mean they are yet to come, waiting for some threshold in the seasonal cycle to be crossed. The patience required to understand Titan is immense. With a Saturn year lasting 30 Earth years, observing a full seasonal cycle would require 3 decades of continuous monitoring. Cassini operated for 13 years, covering less than half a Titan year. We have snapshots of different seasons, but not a complete picture of how the moon changes over time. Mysteries that might be resolved with longer observations remain open. One thing the images have made clear is that Titan is a world of transitions, between the frozen North Pole and the baked equator, between the liquid seas and the dry dunes, between the high organic haze and the icy bedrock below. Everywhere you look, you see boundaries and gradients, places where one type of terrain gives way to another. These transition zones are often the most scientifically interesting places. The boundaries of the lakes, where liquid meets solid. The edges of the dune fields, where sand gives way to other terrain. The margins of the haze layers, where different chemistry dominates. Understanding what happens at these boundaries helps us understand the processes that shape the entire moon. Take the dune margins, for example. At the edges of the great sand seas, the dunes become smaller and more widely spaced. The sand supply is less abundant, so the dunes cannot grow as large. The spacing tells us something about the wind patterns and the availability of sand. By studying how the dunes change at their margins, scientists can infer the conditions in the interior of the sand seas. Similarly, the lake margins reveal the interplay between liquid and land. Where lakes meet the surrounding terrain, you see evidence of erosion, deposition, and chemical interaction. Some shores show what appear to be bathtub rings, marks left by previous lake levels. Others show evidence of flooding, where liquid has spilled out of the lake basin onto the surrounding land. Each of these features tells a story about how the lake has changed over time. The images from Titan also reveal something about time itself. The smoothness of the plains suggests recent resurfacing, perhaps by organic deposits or icy volcanic flows. The sharpness of some impact craters suggests they are relatively fresh, not yet eroded by wind and rain. The presence of active river channels suggests ongoing geological activity. Everything points to a world that is not static but dynamic, changing on timescales that are short by geological standards. Yet there are also hints of great age. The overall structure of the landscape, the distribution of highlands and lowlands, these features may date back billions of years. The deep canyons may have been carved over eons of patient erosion. The organic sediments on the seafloor may represent accumulations spanning vast stretches of time. Titan preserves both recent and ancient histories, layered on top of each other like pages in a book. Reading that book requires patience and skill. Scientists must tease apart the different signals in the data, distinguishing recent events from ancient ones, transient features from permanent ones. The images from Cassini and Huygens are like snapshots, capturing moments in time. But the processes that created those images operate continuously, day after day, year after year, eon after eon. Understanding Titan requires thinking on all these timescales at once. Let us consider what makes these images so haunting, so compelling, so different from images of other worlds. Part of it is the familiarity. When you look at images of Mars, you see a desert world. Beautiful, yes, but clearly different from Earth. Red rocks under a pink sky. Craters and canyons in an environment obviously alien. When you look at images of Europa or Enceladus, you see ice worlds. Gleaming surfaces of frozen water, cracked and fractured in patterns unique to each moon. These worlds are interesting, but they do not look like home. Titan is different. The drainage channels look like rivers. The coastlines look like shorelines. The dunes look like desert landscapes. The haze-filtered light looks like a foggy day. At first glance, you could almost mistake some Titan images for aerial photographs of remote regions on Earth. The resemblance is uncanny, and it triggers something deep in the human brain. A recognition of patterns we know. A sense that this place, however alien, is somehow comprehensible. But then the differences sink in. The rivers run with liquid methane. The shores border seas of natural gas. The dunes are made of organic plastic. The fog is a smog of complex hydrocarbons. The temperature is cold enough to freeze flesh solid in seconds. The resemblance to Earth is superficial, a trick of physics creating similar shapes through similar processes, but with completely different materials. This combination of familiar and alien is what makes Titan so fascinating. It is a mirror world, showing us what Earth might look like if the rules were slightly different, if water were replaced by methane, if rock were replaced by ice, if organic chemistry were a surface process rather than a biological one. Titan shows us Earth through a funhouse mirror, distorted and strange, but still recognizable. The images also evoke a sense of profound loneliness. Titan is so far away. The light we see in the images has traveled over 1 billion kilometers to reach us. At the speed of light, it takes about 1 hour and 20 minutes for a signal to travel between Titan and Earth. When Huygens landed, mission controllers had to wait in suspense for that signal delay before learning the fate of their probe. That distance creates a sense of isolation. Titan orbits Saturn in the cold outer reaches of the solar system. The Sun appears as nothing more than a bright star from that distance, providing only about 1% of the warmth and light that Earth receives. Titan is a world in permanent twilight, bathed in the feeble glow of a distant sun. If you could stand there and look up, you might not even recognize the sun as the same star that blazes overhead on Earth. The loneliness is deepened by the silence. Unlike Earth, with its teeming biosphere and buzzing cities, Titan appears empty. No signals from intelligent life, no movement of animals, no vegetation covering the hills, just rock and ice and organic sludge under an orange sky. The rivers flow without fish. The seas have no whales. The dunes shelter nothing. As far as we can tell, Titan is a world without witnesses, yet there is also grandeur. Titan is a world of scale and majesty. Kraken Mare sprawls larger than the Caspian Sea. The dune fields stretch wider than Canada. The atmosphere reaches higher than Earth's. Mountains rise kilometers above the surrounding plains. This is not a small moon, but a world unto itself, with all the complexity and variety that implies. And beneath that grandeur lies the tantalizing possibility of life. The organic chemistry, the liquid solvents, the subsurface ocean, all the ingredients are there. If life can arise from these ingredients, if chemistry can organize itself into self-replicating systems without our kind of conditions, then Titan might not be as empty as it appears. There might be microscopic organisms we cannot detect. There might be chemistry on the edge of life, poised to take that final step. There might even be things we cannot imagine, life forms so different from our own that we would not recognize them as alive. This uncertainty is part of what makes Titan so compelling. Every image raises as many questions as it answers. Every discovery reveals new mysteries. We have learned so much from Cassini and Huygens, yet we have barely scratched the surface. The real exploration of Titan has not yet begun. Think for a moment about what it means to see these images. Humanity, confined to a single planet for all of its history, has reached out across 1 billion kilometers of space and captured photographs of another world. We have sent our machines to places no human eye has ever seen, and they have sent back visions of alien landscapes that stir the imagination. The Huygens probe represents the farthest landing from Earth ever achieved. When it touched down on Titan's frozen surface, it broke a record that still stands. No human-made object has ever landed farther from home. The probe carried instruments built by engineers and scientists across Europe. It carried the hopes of thousands of people who worked for decades to make the mission possible. And when it landed, it carried all of humanity with it, virtually, into that dim orange world. The images Huygens sent back are precious. Only a few hundred photographs made it through before contact was lost. A coding error meant that half the data Huygens collected was never received by Cassini. What we have is incomplete, fragmentary, a glimpse rather than a comprehensive survey. Yet even these fragments have transformed our understanding of Titan. Consider the first image from the surface. A flat plain strewn with rounded pebbles under an orange sky. The horizon is close, just a few meters away, because the camera was mounted low on the probe. The lighting is dim and diffuse, filtered through hundreds of kilometers of haze. The colors are shades of brown and orange, with no blue or green anywhere to be seen. This image is simultaneously familiar and alien. The pebbles look like river rocks on Earth. Their arrangement suggests the same sorting processes we see in terrestrial riverbeds. But the light is wrong. The colors are wrong. The materials are wrong. Everything we see is made of ice and organics, not rock and soil. The air is cold enough to liquefy oxygen, not warm enough to sustain life as we know it. Looking at this image, you can almost feel the alienness pressing in. This is what an alien world really looks like. Not the science fiction landscapes of television and movies, but something more subtle. A place where familiar patterns emerge from completely different materials. A place that is recognizable yet fundamentally other. The descent images are equally striking. As Huygens fell through the atmosphere, it captured panoramic views of the landscape below. These images show a world of contrasts. Bright highlands give way to dark lowlands. Channels wind down from the heights to the plains below. The patterns repeat at different scales, from kilometers across to just meters. One descent image has become iconic. It shows a network of channels emerging from a bright region and spreading into a darker area that may once have been a lake or sea. The channels are clearly drainage features carved by flowing liquid over time. Their form is unmistakable to anyone who has seen river systems from the air. And yet, this is not Earth. This is Titan, 1 billion kilometers away, where rivers run with liquid methane under skies of nitrogen and smog. These images have a strange power. They make Titan real in a way that no amount of data or description can. When you see the rounded pebbles on the surface, you understand that Titan is a place, not just a concept. When you see the drainage channels from above, you understand that processes are at work there, shaping the landscape in ways we can comprehend. The images bridge the gap between the abstract and the concrete, turning a distant world into a tangible destination. Cassini's radar images have their own character. They are not photographs in the traditional sense. Radar does not capture reflected sunlight, but bounced radio waves. The resulting images are monochrome, with bright areas indicating rough terrain and dark areas indicating smooth surfaces. Liquid appears especially dark because it is smooth and absorbs radar energy. Interpreting radar images requires training and practice. The textures and patterns are different from what we see with our eyes, but once you learn to read them, they reveal Titan's surface in exquisite detail. The sharp edges of crater rims, the smooth expanses of the seas, the repeating patterns of the dune fields, the complex textures of the mountainous regions, all of these become legible when you know what to look for. The resolution of Cassini's radar varies with how close the spacecraft was to Titan during each flyby. The best images resolve features just a few hundred meters across. This is good enough to see individual dunes, to trace the paths of rivers, to map the shapes of lakes, but it is not good enough to see everything. Many details remain hidden, waiting for future missions with better instruments. Some of Cassini's most valuable data came from combining radar with other instruments. The visual and infrared mapping spectrometer, for example, could see through the haze at certain wavelengths of infrared light. Its images are blurry compared to radar, but they provide color information that radar cannot. By combining radar maps with infrared observations, scientists have built up a more complete picture of Titan's surface. The infrared images show Titan's lakes and seas as dark splotches against brighter land. They reveal the different compositions of various surface types. The dunes appear darker than the surrounding terrain because their organic composition absorbs infrared light. The highlands appear brighter because they are made of water ice, which reflects infrared well. These color differences help scientists understand what different regions are made of. One discovery that emerged from combining data sets is the global distribution of surface types on Titan. The equatorial regions are dominated by dunes and plains. The mid-latitudes feature more varied terrain, including mountains and complex networks of channels. The polar regions host the lakes and seas. This banding pattern is similar to climate zones on Earth, suggesting that Titan's weather systems create distinct environments at different latitudes. But there are asymmetries too. The northern hemisphere has far more liquid than the south. The dunes are found mainly in a band around the equator but extend farther north on one side of the globe than the other. These asymmetries hint at complexities in Titan's climate that we do not fully understand. They may be related to Saturn's orbital eccentricity, which affects how much sunlight each hemisphere receives during its summer. Or they may reflect the positions of the poles relative to the prevailing winds. Untangling these factors is an ongoing project for researchers. The study of Titan's surface has revealed something important about planetary science. You cannot understand a world from images alone. You need multiple types of data. Radar to see through the haze, infrared to determine composition, gravity measurements to probe the interior, in situ observations to provide ground truth. Each type of data reveals something different, and only by combining them can you build a complete picture. This is why the loss of half of Huygens' data was so painful. That data might have answered questions we still cannot resolve. It might have provided constraints on models that remain poorly constrained. The coding error that caused the loss was simple, a small bug in the software that controlled the communication link. But its consequences have echoed through decades of subsequent research. Despite these limitations, the images of Titan have inspired a generation of scientists and dreamers. They have spawned proposals for new missions, new instruments, new ways of exploring this enigmatic world. The scientific community has not been satisfied with what Cassini and Huygens provided. They want more. One proposed mission would send a floating probe to one of Titan's seas. This probe would drift on the surface of Kraken Mare or Ligeia Mare, measuring the composition and properties of the liquid. It would monitor waves and currents, if any exist. It would sample the organic material that has accumulated in the sea, and it would take the first photographs from within a body of liquid on another world. Another proposal, now being developed for launch, is called Dragonfly. This mission would send a rotorcraft lander to Titan, a drone-like vehicle capable of flying through the dense atmosphere. Dragonfly would hop from location to location, sampling the surface at multiple sites. It would visit the dune fields to analyze the organic sand. It would visit an impact crater to sample material that has been altered by heat and water. It would measure the composition and chemistry of Titan's surface in ways that have never been possible before. Dragonfly represents a new approach to planetary exploration. Instead of landing once and staying put, it would explore widely, covering tens of kilometers over the course of its mission. This mobility would allow it to investigate the diversity of Titan's surface, visiting sites with different compositions and histories. It is an ambitious mission, pushing the boundaries of what robotic spacecraft can do. The plans for Dragonfly call for it to arrive at Titan in the mid-2030s. If all goes well, it will descend through the haze just as Huygens did 3 decades earlier. But instead of landing once and transmitting for an hour, it will operate for years. It will fly to different locations, taking photographs and measurements at each one. It will build a picture of Titan that makes our current understanding look primitive. Imagine the images Dragonfly might send back. Close-up views of the organic dunes, showing the individual grains that make up the sand. Aerial photographs of river channels and lake shores, captured from just above the surface. Panoramic views of the landscape from mountaintops and crater rims. Each landing site would bring new discoveries, new questions, new opportunities to understand this remarkable world. But Dragonfly is still years away, from launch and more than a decade from arrival. In the meantime, we are left with the images we have, the precious photographs from Huygens, the vast radar maps from Cassini, the infrared observations and gravity measurements, and all the other data that have accumulated over years of study. These images are our window into Titan, our only way to visualize this distant world until new missions arrive. Let us think about what the images tell us about Titan's place in the solar system. Titan is unique. No other moon has a thick atmosphere. No other moon has stable bodies of surface liquid. No other moon has the combination of organic chemistry, weather systems, and geological activity that Titan displays. Among all the moons of all the planets, Titan stands alone. This uniqueness makes Titan valuable for comparative planetology. By studying Titan, we can understand how Earth-like processes operate under different conditions. We can see how rivers form without water, how dunes form without silicate sand, how atmospheres evolve without oxygen. Titan is a natural laboratory for testing our ideas about planetary processes. But Titan is also representative in some ways. It shows us what a world with a nitrogen atmosphere and hydrocarbon chemistry might look like. Such worlds might be common in the universe, orbiting stars in the cold outer reaches of other planetary systems. Titan may be a preview of what we will find when we eventually image exoplanets in detail. The lessons we learn here may apply to countless worlds we have not yet discovered. The images of Titan also remind us of the vastness of the universe. Our solar system is just one of billions in our galaxy. Our galaxy is just one of billions in the observable universe. If Titan, strange as it is exists in our own cosmic backyard, what other wonders might exist farther out? What worlds have we not yet imagined? What sights have never been seen by any eye, human or electronic? This perspective can be overwhelming or inspiring. It can make human concerns seem trivial against the backdrop of cosmic immensity, or it can motivate us to explore, to discover, to push the boundaries of what we know. The choice is ours. But the images of Titan coming from so far away, bearing such strange news, remind us that the universe is bigger and stranger than we often realize. Let us now consider the greatest mystery that the images of Titan present. The question that hangs over all our observations. The puzzle that future missions hope to solve. Is there life on Titan? We have discussed the possibilities. Methanogenic organisms on the surface, breathing hydrogen and eating acetylene. Life in the subsurface ocean, swimming in water and ammonia far below the ice. Exotic life forms we cannot imagine, using chemistry we have never seen. The ingredients are there. The conditions might be right, but we have no proof one way or the other. The images cannot answer this question directly. You cannot see microscopic organisms in radar maps or infrared photographs. Even close-up images from Huygens showed only rocks and pebbles, not living things. If life exists on Titan, it is not obvious from the pictures we have taken. But the images can guide the search. They show us where the interesting environments are. The shores of the lakes where liquid meets solid. The organic dunes where complex chemistry abounds. The impact craters where water ice has been melted and mixed with organics. These are the places where life might be found, if it exists at all. The choice of landing sites for Dragonfly reflects this logic. The mission will visit Selk Crater, a site where an ancient impact created conditions favorable for prebiotic chemistry. Water ice was melted by the impact, creating temporary pools of liquid. That liquid mixed with the organic material on Titan's surface. Chemical reactions occurred that might have produced biologically interesting molecules. Even if those molecules never became life, they represent a step along the path from simple chemistry to complex biochemistry. Dragonfly will sample the material in and around Selk Crater. It will analyze the composition and look for signs of complex organic molecules. It will search for any indication that chemistry has progressed beyond what we would expect from purely abiotic processes. Finding such signs would not prove that life exists, but it would suggest that conditions on Titan are capable of producing life-relevant chemistry. The search for life on Titan is hampered by our lack of imagination. We know what life looks like on Earth. We know the chemistry it uses, the structures it builds, the signatures it leaves. But life on Titan, if it exists, might be completely different. It might use solvents and reactants we have never considered. It might leave traces we would not recognize as biological. It might be so alien that we would not know we had found it. This is both humbling and exciting. Humbling because it reminds us that our knowledge is limited. We are looking for life based on what we know, but what we know is based on a sample size of 1. Earth life is the only life we have ever studied. Everything we think we know about biology might be parochial, specific to our particular evolutionary history. Life elsewhere might play by completely different rules, but it is also exciting because it opens up possibilities. If life is not limited to the chemistry we know, then it might be far more common than we have assumed. It might arise wherever conditions permit complex chemistry, regardless of the specific substances involved. It might be a universal phenomenon, as fundamental to the cosmos as stars and galaxies. Titan, with its alien chemistry and familiar processes, is one of the best places to test this hypothesis. The images of Titan plant this question in our minds. When you look at the rivers and lakes, you cannot help but wonder what might live there. When you see the organic dunes stretching to the horizon, you imagine microscopic things crawling among the grains. When you think about the subsurface ocean, hidden beneath kilometers of ice, you picture vast communities of organisms thriving in eternal darkness. These imaginings may be correct or completely wrong. We simply do not know. But the images make the question vivid. They show us a world where life might exist, a world different enough from Earth to challenge our assumptions, yet similar enough to seem almost plausible. Titan is not just a moon. It is a question mark, a challenge to everything we think we know about the nature of life. The story of Titan, as told through these images, is far from over. We have learned much, but we have much more to learn. The next chapter will be written by new missions, new instruments, new generations of scientists and explorers. The images we have now are like the first sketches of a vast landscape. They hint at what is there, but they do not capture the full reality. Future images will be sharper, more detailed, more comprehensive. They will show us things we cannot see now. They will answer questions we have been asking for decades, and they will raise new questions we have not yet thought to ask. That is the nature of exploration. Each discovery opens new doors, reveals new mysteries, sends us deeper into the unknown. The images of Titan are an invitation. They invite us to imagine, to wonder, to question. They invite us to build spacecraft and send them to distant worlds. They invite us to push against the limits of what we know and see what lies beyond. They are not just data or documentation. They are a call to adventure. When you look at a photograph of Titan's surface, you are looking at a place no human has ever seen with their own eyes. A place where no human footprints mark the ground. A place where the only sign of our existence is the probe we sent, now silent and frozen on that distant plain. The image is a message from the frontier, a postcard from the edge of human knowledge. And that frontier is calling. It has been calling since the first images came back, showing us glimpses of a world beyond imagination. It calls to scientists who spend their careers puzzling over the data. It calls to engineers who design the spacecraft that gather that data. It calls to students who dream of one day contributing to the exploration. It calls to all of us who look up at the night sky and wonder what is out there. Titan is waiting. Its secrets are still locked away, hidden beneath that orange haze. But we have glimpsed enough to know that the answers are worth seeking. We have seen enough to know that this world has stories to tell. And we have come far enough to know that we can, eventually, with patience and persistence, uncover those stories. The real images of Titan show that something is off about this world. They show landscapes that look like Earth but are made of alien materials. They show weather systems that operate on completely different chemistry. They show geological processes that create familiar shapes from unfamiliar substances. They show a world that mirrors our own while being utterly, fundamentally different. That strangeness is what draws us in. It challenges our assumptions and expands our horizons. It reminds us that the universe is vast and varied, full of wonders we have not yet discovered. Titan is one of those wonders, revealed through the images we have captured, waiting for us to learn more. As you drift off tonight, perhaps you will dream of that orange world. You will see the pebble-strewn plains under dim orange skies. You will see the rivers of liquid methane winding through icy highlands. You will see the vast dark seas reflecting the dim glow of a distant sun. You will feel the thick atmosphere pressing around you, hear the silence of a world without human voices. And somewhere in that dream, you might catch a glimpse of something unexpected. A movement among the dunes, a ripple on the surface of a sea, a hint of something alive in a world that should be dead. Perhaps it is just your imagination, or perhaps it is a premonition of discoveries yet to come. Titan does not give up its secrets easily, but the images we have are the beginning of a story that will unfold over decades and centuries. Each mission builds on the last. Each discovery opens new paths of inquiry. The strange world beneath that orange haze is slowly coming into focus, revealing itself one image at a time. We are privileged to live in an era when such images are possible. Our ancestors could only imagine what lay among the stars. We can actually see it. The robots we send outward are extensions of our senses, bringing back visions of places we cannot physically visit. Through their cameras and instruments, we have touched the surface of Titan. We have seen what waits there, and we have begun to understand. The images of Titan are more than scientific data. They are a testament to human curiosity, human ingenuity, human perseverance. They represent thousands of hours of work by thousands of people over decades of effort. They are the fruit of collaboration across nations and generations. They are a gift from the past to the future, a legacy that will endure long after the spacecraft that captured them have fallen silent. So look at those images. One more time. See the strange landscapes and alien features. Appreciate the vastness of the distance they have traveled to reach your eyes. Consider the mysteries they contain and the questions they pose, and know that you are connected through those images to one of the most remarkable worlds in our solar system. Titan is out there, circling Saturn in the cold darkness of the outer solar system. Its seas of liquid methane reflect the dim light of a faraway sun. Its dunes of organic sand stretch toward hazy horizons. Its hidden ocean waits beneath kilometers of ice, and its secrets, vast and profound, remain to be discovered. The journey to Titan has only just begun. The images we have are a preview of what awaits, and the story they tell of a world both alien and familiar is one that will captivate us for generations to come. As our exploration of this cosmic mirror continues, we will undoubtedly find more surprises, more features that challenge our expectations, more evidence of processes we did not anticipate, more questions to replace the ones we answer. That is the way of science, the way of discovery, the way of the endless human quest to understand the universe we inhabit. The real images of Titan reveal a world where something is profoundly off, profoundly different, profoundly mysterious. But they also reveal a world that is beautiful, complex, and worthy of our attention. In the end, that may be the most important message the images convey. Not that Titan is strange, but that it is magnificent, a world of wonder waiting for us to explore. Thank you for joining us on this journey through the images of Titan. The mysteries of Saturn's largest moon continue to unfold with each passing year. As we await new missions and new discoveries, take a moment to marvel at how far we have come and how much remains to be learned. If you enjoyed this exploration, please consider liking this video and subscribing to Cosmic Drift for more journeys through the cosmos. Share your thoughts about Titan in the comments below. What do you find most fascinating about this strange mirror world? What questions would you most want answered by future missions? Until next time, keep looking up at the stars. Keep wondering about the worlds that orbit them. and keep dreaming of the day when we might see those worlds with our own eyes. Sweet dreams, fellow travelers. May your journey through the cosmos be filled with wonder. But before we conclude this journey, let us return to some of the specific features revealed in Titan's images and explore them more deeply. There is so much richness in the data we have collected that even after hours of discussion, we have only scratched the surface of what these images reveal. Consider the question of how Titan's surface evolved over time. The images show us a snapshot of the present, but that present is the product of billions of years of geological and atmospheric processes. Understanding how we got from the formation of Saturn's moons to the Titan we see today requires piecing together clues scattered across the landscape. When Titan first formed, it was likely a simpler world. The solar system was young, and the processes that would shape this moon had barely begun. The atmosphere was different, perhaps thinner or composed of different gases. The surface was covered in fresh ice, unweathered by the organic rain that would eventually blanket it. The interior was hotter, still retaining heat from formation and radioactive decay. Over billions of years, that initial state transformed into what we see today. The atmosphere evolved as nitrogen and methane were processed by sunlight. The organic haze developed, gradually thickening until it blocked all visible light from reaching the surface. The ice crust cooled and solidified, perhaps developing the subsurface ocean as temperatures dropped to the point where pure water could not remain liquid, but ammonia-water mixtures could. The surface features we observe tell stories of this evolution. The impact craters that remain date from different eras, their modification by erosion revealing how long they have been exposed to Titan's weather. The channels and rivers indicate a long history of liquid flow, carving ever deeper into the substrate. The dunes represent accumulation over timescales we can barely comprehend, particle by particle, building up from the constant rain of organic material. One particularly intriguing feature is the vast, dark region called Shangri-La. This sprawling expanse of dunes stretches across thousands of kilometers near Titan's equator. The name comes from the mythical utopia, but Shangri-La on Titan is no paradise. It is a desert of organic sand, cold and dark and utterly lifeless as far as we can tell. The dunes of Shangri-La are arranged in long parallel ridges that run roughly east to west. Their spacing and orientation tell us about the winds that shape them. The dominant winds on Titan blow from east to west, driven by the rotation of the moon and the heating of its atmosphere. But the dunes form from west to east, opposite to the wind direction. This apparent paradox is explained by occasional stronger winds that blow in the opposite direction, rearranging the sand during rare storm events. The individual dunes in Shangri-La are impressive structures. Some exceed 100 kilometers in length, stretching from one horizon to the other in what would be a breathtaking sight if any observer were present to see them. They rise to heights of roughly 100 meters, towering walls of organic material that would dwarf most buildings on Earth. Walking across these dunes, if such a thing were possible, would be a surreal experience. The sand beneath your feet would not be made of familiar silicate grains, but of complex organic molecules, hydrocarbons and nitriles in combinations we have barely begun to characterize. The texture might be different from Earth sand. Some scientists describe it as similar to coffee grounds, while others suggest it might be more like fluffy snow that has been compacted over time. The darkness of the dunes is notable. In radar images, they appear much darker than the surrounding terrain because their composition absorbs radar energy rather than reflecting it. This absorption tells us something about the material. It is probably composed of organic molecules with carbon-carbon bonds and nitrogen-containing functional groups. These are the same types of molecules that make up living things on Earth, though on Titan they exist without any known biological origin. Between the dune ridges lie the interdunes, the valleys that separate one dune from the next. These interdune areas show different radar signatures than the dunes themselves, suggesting different surface properties. Some interdunes appear to be floored with coarser material, larger organic grains that the wind cannot easily move. Others may be covered with a thin layer of frost or condensed organics from the atmosphere. The dune fields do not extend to all parts of Titan. They are concentrated in the equatorial band between about 30 degrees north and 30 degrees south. Beyond these latitudes, the terrain changes character. The dunes give way to plains and then to the lake-studded polar regions. This distribution reflects the climate of Titan, with the dry equatorial region favoring dune formation, while the wetter poles support bodies of liquid. Another feature worth examining more closely is Sotra Patera, a possible cryovolcanic complex in Titan's southern hemisphere. This region includes two mountains, Doom Mons and Erebor Mons, a large depression that may be a volcanic caldera, and what appear to be flow features spreading outward from the central area. Cryovolcanism is the eruption of materials that are typically solid at the cold temperatures of the outer solar system, but become liquid or gaseous under certain conditions. On Titan, this would likely involve water and ammonia, which together can remain liquid at temperatures well below 0 degrees Celsius. If eruptions of this water-ammonia mixture have occurred at Sotra Patera, they would have spread across the surface before freezing, creating the flow features we observe. Between 2005 and 2006, scientists noticed that parts of Sotra Patera had become brighter in the images. The surrounding plains had not changed, but the volcanic complex itself was more reflective than before. This could indicate fresh material on the surface, potentially from an eruption that occurred during the observation period. If so, it would be evidence that Titan's cryovolcanism is ongoing, not just a relic of the past. The implications of active cryovolcanism are significant. It would provide a mechanism for replenishing methane in the atmosphere, solving one of Titan's enduring mysteries. It would indicate that the interior of the Moon is still geologically active, with heat and material being transferred from the depths to the surface, and it would create temporary environments where liquid water might exist, mixing with organic material and potentially enabling prebiotic chemistry. But the evidence for cryovolcanism on Titan remains debated. Some scientists argue that the features at Sotra Patera and elsewhere could have formed through other processes, such as erosion or tectonics. The brightness changes could be explained by atmospheric effects rather than surface eruptions. More data is needed to resolve the question, data that future missions may provide. Let us turn now to the smaller lakes that dot Titan's polar regions. While Kraken Mare, Ligeia Mare and Punga Mare attract the most attention due to their size, hundreds of smaller lakes have been identified in the radar images. These lakes range from tiny ponds just a few kilometers across to substantial bodies dozens of kilometers wide. The distribution of these smaller lakes is interesting. They cluster in certain areas, forming lake districts not unlike those found in some regions of Earth. Minnesota, for example, is known for its 10,000 lakes. scattered across the landscape as a legacy of past glaciation. Titan's lake districts may have formed through different processes, but the resulting pattern is visually similar. Many of the smaller lakes have sharp-edged, irregular outlines. They look like they have been stamped into the landscape, with steep sides dropping suddenly to the liquid surface. This morphology has led some scientists to propose that they form through a process similar to karst topography on Earth. In karst landscapes, soluble rock like limestone is dissolved by groundwater, creating sinkholes, caves, and lakes with distinctive shapes. On Titan, the soluble material would not be limestone but organic compounds or possibly even water ice. The solvent would not be water but liquid hydrocarbons. Over time, this dissolution would create depressions that fill with liquid, producing the lakes we observe. If this hypothesis is correct, it suggests that complex chemical interactions are occurring between Titan's surface and its liquid hydrocarbons. Some of the lakes show elevated rims, raised areas surrounding their edges. These could be deposits left behind as liquid evaporated, or they could be the remains of material that was pushed aside as the lake basin formed. On Earth, some crater lakes have similar raised rims where ejected material piled up during the impact. But Titan's lake rims do not seem to be associated with impacts. They may instead be evidence of constructional processes, material being built up rather than excavated. The depths of the smaller lakes are largely unknown. Radar signals can penetrate shallow liquid and bounce off the bottom. But for lakes more than a few tens of meters deep, the signal is absorbed before reaching the floor. Most of Titan's smaller lakes appear to be shallow enough for radar to measure, with depths typically less than 10 meters. But some show no bottom return at all, suggesting either greater depth or a different composition that absorbs radar more effectively. One curious observation is that many lakes in the north appear to be filled to the brim. Their surfaces are at the same level as the surrounding terrain, as if they have been topped up to the maximum possible extent. This suggests that something is regulating the lake levels, perhaps the same process that maintains the stability of the larger seas. Groundwater seepage, atmospheric evaporation and precipitation, and connections between different liquid bodies could all play a role in this regulation. In contrast, some lakes appear to be only partially filled, with visible bathtub ring features marking previous higher levels. These indicate that liquid levels have dropped over time, either due to seasonal evaporation or longer-term climate changes. By measuring the extent of these shoreline marks, scientists can estimate how much the lakes have shrunk and potentially correlate these changes with other observations. The difference between filled and partially filled lakes may relate to their positions in the landscape. Lakes at lower elevations are more likely to be filled because liquid drains toward them from surrounding areas. Lakes at higher elevations may receive less inflow and therefore be more susceptible to evaporation. The pattern we observe is consistent with a hydrological system in which liquid flows downhill, accumulating in the lowest available basins. Moving from the surface to the atmosphere, the images have also revealed much about Titan's weather systems and atmospheric structure. The haze layers visible in some images extend to extraordinary heights, far above the surface. The main haze layer sits at about 200 to 300 kilometers altitude, a global blanket of organic particles that gives Titan its characteristic orange color. Above this main haze, a detached layer has been observed at around 400 to 500 kilometers altitude. This layer is thinner and more variable than the main haze below. Its presence suggests that atmospheric chemistry and dynamics are occurring at multiple levels, with particles forming and settling at different altitudes. The haze shows seasonal variations. During Titan's winter, one pole is tilted away from the sun and receives less energy. The atmosphere cools in that region, and the haze appears to intensify. A polar vortex can form, concentrating haze particles and trace gases in a swirling pattern above the winter pole. These vortices have been observed moving and changing as the seasons progress, providing evidence of dynamic atmospheric circulation. The transition from northern winter to northern summer, which occurred during the Cassini mission, produced observable changes in Titan's atmosphere. The northern polar vortex dissipated as spring arrived, while a new vortex began forming over the South Pole as it entered autumn. These changes unfold slowly on human timescales, but demonstrate that Titan's weather is not static. It responds to the changing input of solar energy, just as Earth's weather does. The chemistry occurring in Titan's atmosphere is extraordinarily complex. When ultraviolet light strikes methane molecules in the upper atmosphere, it breaks them apart. The resulting fragments, highly reactive radicals, immediately start combining with other molecules. Carbon atoms link together to form longer chains. Nitrogen atoms from the abundant atmospheric nitrogen get incorporated into the mix. The result is a cascade of reactions producing hundreds or thousands of different compounds. Some of these compounds condense and form the particles that make up the haze. Others remain gaseous and circulate through the atmosphere. Still others are destroyed by subsequent chemical reactions before they can accumulate. The atmosphere is a gigantic chemical reactor, continuously processing its ingredients and producing new outputs. Among the products detected in Titan's atmosphere are benzene, the simplest aromatic hydrocarbon, and hydrogen cyanide, a molecule that has been implicated in prebiotic chemistry on early Earth. The detection of these specific compounds is significant because they are stepping stones to more complex molecules. Benzene can serve as a foundation for larger ring structures. Hydrogen cyanide can participate in reactions that produce amino acids and nucleotide bases. The presence of these molecules does not mean life is forming in Titan's atmosphere, but it does mean the chemistry is progressing in a direction that could potentially lead toward life. The atmosphere is creating the building blocks, assembling the components that more complex systems might eventually use. Whether those building blocks ever assemble into something alive is a question we cannot yet answer. The images from Titan also include views of Titan from above, showing the entire disk of the Moon from space. These global views reveal the overall structure of the atmosphere, the distribution of surface features, and the relationship between different regions. They provide context for the detailed images of specific locations, showing how each piece fits into the larger puzzle. From above, Titan appears as a fuzzy orange sphere. The haze softens all the features, blurring boundaries and muting contrasts. Only in certain infrared wavelengths can you see through to the surface, and even then the view is hazy compared to what you would see on an airless world. The thick atmosphere both protects and obscures, maintaining Titan's secrets even as we peer down from orbit. The North Pole region, with its concentration of lakes and seas, appears darker than the rest of the disk when viewed in radar or certain infrared bands. This is because liquid absorbs radiation, while solid surfaces reflect it. The South Pole appears different, with fewer dark patches indicating less surface liquid during the season when Cassini observed it. The equatorial band appears brighter in some wavelengths due to the reflective properties of the organic sand dunes. The mid-latitudes show a mixture of terrains, with variable brightness depending on the specific locations being viewed. These global patterns confirm what the detailed images show. Titan's surface is not uniform but divided into distinct climate zones, each with its own characteristic features. One of the most beautiful images from the Cassini mission shows Titan silhouetted against Saturn, the larger planet filling most of the frame. The Moon appears as a small orange disk, its atmosphere glowing with scattered sunlight, while Saturn's massive form stretches behind it. The image captures the scale of the Saturn system, showing tiny Titan dwarfed by the planet it orbits. Another striking image shows Titan's night side, illuminated by light scattered through its atmosphere. The Moon appears as a blue ring, the sunlight bending through the atmosphere and creating a glowing halo around the dark disk. This blue color comes from scattering of shorter wavelengths by the upper atmosphere, the same phenomenon that makes Earth's sky blue. It is a reminder that despite all its differences, Titan is subject to the same physics as our own world. These images from space complement the surface views, providing a sense of Titan as a complete world rather than just a collection of features. They show the Moon in its cosmic context, orbiting a giant planet in the cold outer reaches of our solar system. They remind us of the vast distances involved and the remarkable achievement of sending spacecraft to capture these views. The combination of orbital images and surface data has allowed scientists to build three-dimensional models of Titan's topography. By analyzing radar returns and correlating them with other data, researchers can map the heights and depths of surface features. Mountains, craters, lake basins, and plains all emerge from this analysis, creating a virtual globe of Titan that can be explored and studied. These topographic maps reveal that Titan is a relatively smooth world compared to some other moons. There are no towering peaks like those found on some of Jupiter's moons. The highest mountains rise only a few kilometers above the surrounding terrain. The deepest basins, including the lake beds, are also relatively shallow. Titan's ice shell may be too weak to support extreme topography, flowing slowly over time and leveling out any features that rise too high or sink too deep. The smoothness of Titan's surface is consistent with an active world that reshapes itself over time. Erosion wears down highlands. Deposition fills in lowlands. Geological activity may resurface areas with fresh material. The result is a landscape that is never far from equilibrium, with most features within a few kilometers of the mean surface level. This is very different from a dead world like our Moon, where features created billions of years ago remain essentially unchanged. Ancient craters on the lunar surface are still visible, their outlines sharp and their interiors preserved. On Titan, such ancient features would have been erased long ago, buried beneath organic deposits or worn away by wind and rain. The contrast between active and inactive worlds raises interesting questions about habitability. Life as we know it requires change, requires energy flows, requires environments that are not in perfect equilibrium. A dead world offers no opportunities for metabolism, no energy gradients to exploit, no pathways for chemical evolution. An active world like Titan provides all of these, at least in principle. Whether Titan's activity is sufficient to support life remains unknown. The energy available from hydrocarbon chemistry is limited compared to what photosynthesis provides on Earth. The temperatures are extremely cold, slowing chemical reactions by factors of millions compared to Earth temperatures. The solvents available are less effective than water at enabling the complex chemistry life requires. Yet the images suggest that something is happening on Titan. The surface is changing, material is moving, chemistry is proceeding. Whether any of this activity has crossed the threshold from complex chemistry to life is a question for future missions to investigate. As we near the end of this exploration, let us consider one more time what the images of Titan mean for our understanding of the cosmos. For most of human history, other worlds were abstractions, points of light in the sky, moving according to mathematical laws, but otherwise unknown. Even after telescopes revealed these points as disks with features, other worlds remained fundamentally mysterious. We could speculate about what they might be like, but we could not know for certain. The space age changed that. We sent probes to other planets and moons, and they sent back images. Suddenly, other worlds were no longer abstractions but places. Real places with real features that could be mapped and studied. The images made these worlds concrete in a way that numbers and measurements never could. Titan represents one of the most dramatic examples of this transformation. Before Cassini and Huygens, Titan was little more than an orange blur. We knew it had an atmosphere. We knew it was large. We could guess at what might lie beneath the haze. But we could not see it. We could not know it as a place. Now we can. The images have revealed mountains and rivers, seas and dunes, weather systems and geological processes. They have shown us a world that is strange and wonderful, alien, and yet somehow familiar. They have transformed Titan from a mystery into a destination. This transformation matters because it changes how we think about the universe. When other worlds were abstractions, it was easy to see Earth as special, as unique, as the only place that mattered. But when you can look at images of rivers on Titan and recognize the same patterns you see on Earth, something shifts. You realize that the processes that shape our world are not unique to our world. They operate elsewhere, creating similar features under different conditions. This realization is humbling. We are not alone in having an interesting world. The universe is filled with interesting worlds. What we do not know is whether any of those worlds harbor life. Titan's images bring this question into sharp focus. Here is a world with liquids and organic chemistry, weather and geological activity. All the ingredients seem to be present, yet we have no evidence that life has arisen there. Perhaps life is rare, requiring very specific conditions that Titan does not quite meet. Perhaps life is common but takes forms we would not recognize or cannot detect. Perhaps life is waiting to emerge, poised at some threshold that has not yet been crossed. The images cannot answer these questions. They can only show us the stage on which the drama might unfold. The coming years will bring new missions and new images. Dragonfly will land on Titan and explore its surface in ways that have never been possible. It will analyze the organic material, search for signs of complex chemistry, and test hypotheses about habitability. The images it sends back will add new chapters to the story we have begun to tell. And beyond Dragonfly, who knows what missions may follow? Submarines to explore the depths of Kraken Mare, balloons to float through the atmosphere and observe from above, landers to investigate specific sites of interest. Each mission will build on what came before, adding detail and nuance to our understanding. The images of Titan are not the end of a story, but the beginning. They have revealed a world worth exploring, a place that challenges our assumptions and expands our horizons. They have shown us that the universe is stranger and more wonderful than we imagined. and they have invited us to learn more, to keep looking, to keep asking questions. That invitation stands open. Titan is waiting. Its secrets are vast, its mysteries profound. The images we have are like glimpses through a window, revealing just enough to make us want to see more. What lies beyond the horizons we have mapped? What processes are occurring in the depths we have not probed? What surprises await the next generation of explorers? We do not know, and that is precisely why Titan matters. It reminds us that the universe is not fully known, that discovery is still possible, that the frontier is still open. In an age when so much seems settled and understood, Titan offers the thrill of genuine mystery. Something is off about this world, something that defies easy explanation. Understanding what that something is will require patience, ingenuity, and a willingness to be surprised. The real images of Titan show us a frozen, foggy world beneath an orange sky, a world of methane seas and organic dunes, a world where rain falls from hydrocarbon clouds and rivers carve canyons through ice, a world that mirrors Earth in the strangest ways while being utterly, fundamentally different. These images are a gift. They are the fruit of decades of work by thousands of people, a testament to human curiosity and capability. They belong not just to the scientists who collected them, but to all of humanity. They are our eyes looking outward, our consciousness reaching toward the stars. So remember these images as you drift off to sleep tonight. Remember the rounded pebbles on that alien shore. Remember the vast dark seas under dim orange skies. Remember the towering dunes of organic sand, stretching to invisible horizons. Remember that out there, 1 billion kilometers away, a strange and beautiful world is waiting. And dream of what we might discover when we finally go back. The story of Titan is far from over. The images we have gathered are merely the prologue to a much longer tale. In the decades ahead, new spacecraft will venture to this distant moon. New instruments will probe its atmosphere and surface. New discoveries will reshape our understanding of what is possible in the cosmos. Until then, we have these images, these precious glimpses of another world. They show us that something is off about Titan, something that makes it unlike any other place we have explored. But they also show us that the universe is knowable, that its secrets can be uncovered through patience and persistence. The real images of Titan are an invitation to wonder, to explore, to dream. Accept that invitation. Look at those images with fresh eyes. See the patterns and mysteries they reveal, and know that you are connected, through those images, to one of the most remarkable worlds in our solar system. Titan awaits. Its stories are still being written, and somewhere in those stories, answers to our deepest questions may be hiding. Sweet dreams, fellow travelers. The cosmos is vast and full of wonders. Tonight, let Titan's mysteries carry you into peaceful slumber. Tomorrow, the exploration continues. Let us take one final journey through the most compelling aspects of Titan's images before we conclude. The interplay between Titan's atmosphere and surface creates feedback loops that we are only beginning to understand. Methane evaporates from the seas, rises into the atmosphere, gets converted into more complex hydrocarbons, falls back to the surface as organic rain, accumulates in the dune fields, and eventually washes back into the seas through river systems. This cycle has been operating for billions of years, slowly but relentlessly reshaping the moon's face. Consider what this means for the total amount of organic material on Titan. The dune fields alone contain more organic carbon than all of Earth's proven oil reserves. The seabed sediments add more still. The atmospheric haze represents a constant flow of organic particles descending from the sky. And buried beneath the surface, in deposits we cannot see, there may be even more. If you could somehow collect all the organic material on Titan and bring it to Earth, it would represent a treasure beyond measure. Not because hydrocarbons have economic value, but because they represent the raw materials from which life might arise. Titan is drowning in the stuff of life. Carbon, hydrogen, nitrogen, all bound together in complex arrangements that took billions of years to form. The question that haunts every researcher who studies these images is whether any of that organic material has organized itself into something alive. The chemistry is there, the energy sources are there, the liquid solvents are there. All the prerequisites for life, as far as we understand them, exist on Titan. What we do not see, what we cannot see from our current vantage point, is whether that final step has been taken. The search for life on Titan faces unique challenges. On Mars, we can look for fossils, for biosignatures in rock, for residues of past biological activity. Mars had liquid water in the past, and the geology preserves traces of that era. On Europa or Enceladus, we can analyze plumes of water vapor that erupt from subsurface oceans, looking for chemical signs of life. But Titan offers neither of these opportunities. Its surface is constantly resurfaced by organic deposits and weather processes. Any fossils would be buried or destroyed. Its subsurface ocean is locked away beneath kilometers of ice, inaccessible to current technology. If life exists on Titan, finding it will require new approaches, new instruments, new ways of thinking about what biological signatures might look like. One approach focuses on isotopic ratios. Living things on Earth preferentially incorporate certain isotopes of carbon and other elements into their tissues. This preference leaves a characteristic signature that can distinguish biological from non-biological carbon. If life on Titan uses similar isotopic preferences, we might be able to detect its presence by analyzing the carbon isotopes in surface materials. Another approach looks for chemical disequilibrium. Living things maintain their internal environments in states far from chemical equilibrium. They pump ions across membranes, build complex molecules, and resist the tendency toward entropy that dominates non-living matter. If life exists on Titan's surface, it might create local patches of chemical disequilibrium that instruments could detect. A third approach searches for patterns. Life tends to create regular patterns, from the hexagonal cells of honeycombs to the spiral arms of shells. If microscopic life exists in Titan's organic deposits, it might leave trace patterns that careful analysis could reveal. This approach is speculative, but it represents the kind of creative thinking that exploring alien worlds requires. The images from Cassini and Huygens cannot address these questions directly. They lack the resolution to see microscopic features. They cannot analyze isotopic ratios or chemical equilibria. They show us the large-scale structure of Titan's surface, but not the molecular-scale processes that might indicate life. What the images can do is guide future exploration. They show us where the interesting environments are. They identify locations where liquid and organic material come together. They reveal the diversity of Titan's surface and the range of conditions that exist there. Armed with this knowledge, mission planners can choose landing sites that maximize the chance of detecting life if it exists. The selection of Selk Crater as Dragonfly's primary landing site reflects this logic. Selk is an impact crater about 80 kilometers in diameter, located near Titan's equator. The impact that formed it melted substantial amounts of water ice, creating a temporary pool of liquid water that mixed with Titan's abundant organic material. If prebiotic chemistry occurred anywhere on Titan's surface, Selk is a prime candidate. The images show Selk as a roughly circular feature with a central peak, similar to craters on other worlds. Its floor appears to be covered with dark material, probably organic deposits that have accumulated since the crater formed. The rim is partially eroded, suggesting the crater is old enough to have been modified by Titan's weather, but young enough to still be recognizable. What makes Selk special is not its appearance, but its history. For a brief period after the impact, conditions at Selk would have been similar to those that may have given rise to life on early Earth. Warm liquid water, abundant organic material, energy from chemical reactions, all the ingredients mixed together in a cosmic cauldron. If anything interesting was going to happen, it would have happened there. Dragonfly will land at Selk, sample the material on and around the crater, and analyze it with sophisticated instruments. It will look for amino acids, nucleotide bases, and other molecules associated with life. It will search for patterns in the chemistry that might indicate biological activity. And it will take images far more detailed than anything Cassini or Huygens could provide. These future images will add new dimensions to our understanding. Where we now see a dark smudge in radar maps, we will see individual grains of organic material. Where we now see generalized terrain types, we will see specific mineralogy and chemistry. The transformation will be as dramatic as the one that occurred when Cassini first penetrated Titan's haze. But even with Dragonfly, much will remain unknown. A single lander, no matter how capable, can only explore a tiny fraction of Titan's vast surface. It will visit a few locations, take a few samples, answer a few questions. Many more locations will remain unvisited. Many more samples will remain uncollected. Many more questions will remain unanswered. The full exploration of Titan will require many missions over many decades. Orbiters to map the surface in greater detail. Landers to investigate specific sites of interest. Perhaps even flotillas of small probes scattered across the surface to provide simultaneous measurements from many locations. The images we have today are just the beginning of a long process of discovery. And beyond the scientific exploration, there is the question of human presence. Could people ever visit Titan? Could humans walk on that strange surface, breathe air pumped from insulated habitats, look up at Saturn hanging huge in the orange sky? The challenges would be immense. Titan is far from Earth, requiring years of travel even with advanced propulsion. The cold is so extreme that ordinary materials become brittle and fail. The lack of oxygen means no external source of breathable air. The radiation environment near Saturn poses health risks for unshielded humans. Yet Titan also offers advantages that no other destination in the outer solar system can match. Its thick atmosphere provides protection from radiation and micrometeorites. Its surface gravity, though low, is enough to prevent the bone loss that afflicts astronauts in microgravity. Its hydrocarbon resources could potentially be converted into fuel and other useful materials. And its density means aircraft could fly without exotic propulsion systems, using simple wings to soar through the thick air. Some visionaries have even suggested that Titan might be more suitable for human colonization than Mars. The atmospheric pressure is close to Earth's, eliminating the need for heavy pressure suits. A simple oxygen mask would allow someone to walk on the surface, protected only from the cold. The resources available, both organic and inorganic, could support an industrial civilization. These ideas remain speculative, far beyond current technology or budget realities. But they remind us that Titan is not just a scientific curiosity. It is a potential destination, a place that humans might one day call home. The images we capture today may guide not just robotic explorers, but eventually human pioneers. Imagine standing on Titan's surface a century from now. Behind you, a habitat dome glows with interior lights, the only bright colors in a landscape of muted oranges and browns. Before you, the terrain stretches to a horizon that seems closer than it would on Earth, due to Titan's smaller size. Above, Saturn's bulk dominates the sky, its rings tilted at whatever angle the season dictates. You walk across that surface, your footprints the first human marks on this alien ground. The sand crunches beneath your boots, organic grains compacting under your weight. The cold seeps through your suit despite its insulation, a reminder of how hostile this environment truly is. But you are here, present, experiencing firsthand what cameras and instruments could only hint at. This future is not guaranteed. It depends on decisions yet to be made, technologies yet to be developed, priorities yet to be established. But the images of Titan keep that future alive as a possibility. They show us a world worth reaching, a destination worth the effort and expense and risk of sending humans beyond Earth. The real images of Titan are, thus, more than scientific data. They are invitations to imagine, to plan, to dream. They connect us to a future we may never see, but can still influence. They represent human ambition made visible, our reach extending toward the stars. As this exploration comes to a close, take a moment to appreciate what we have accomplished. We have sent robots across 1 billion kilometers of space to photograph a world no human eye has ever seen. We have mapped landscapes that existed in darkness since the formation of the solar system. We have discovered seas and rivers and dunes on a moon that most people cannot even name. This is remarkable. This is unprecedented in human history. This is something to celebrate. And yet it is only the beginning. The images we have raise more questions than they answer. They show us enough to know that Titan is fascinating, but not enough to satisfy our curiosity. They are windows that reveal glimpses of a vast mansion we have only begun to explore. The story of Titan will continue to unfold as new missions arrive, and new images stream back to Earth. Each discovery will add to our understanding. Each puzzle solved will reveal new puzzles to pursue. The process is endless as human curiosity itself. So rest now, and let the images of Titan fill your dreams. See the orange haze parting to reveal mountains and plains below. See the methane seas glinting under the dim light of a distant sun. See the rivers winding through dark canyons carved in water ice. See the dunes marching across the equator in endless parallel ranks. This is Titan. This is Saturn's largest moon. This is a world where something is profoundly, mysteriously off. And this is a world that awaits your curiosity, your imagination, your dreams of exploration. The images are real. The world they show is real. And the invitation they extend is real as well. Come explore with us. Come wonder with us. Come dream of what lies beyond the next horizon. Titan is calling. Its images are the first words of a conversation that has only just begun. What will we discover when we listen more closely? What secrets will reveal themselves as our instruments grow more sophisticated? What answers will emerge from the fog of the unknown? We cannot say, but we can watch and wonder and prepare. The images of Titan have shown us that something strange is happening on that distant moon. Understanding what that something is will be the work of generations, but the journey has begun, and the first steps have been taken. And that, perhaps, is the most important thing the images tell us. Not that Titan is strange, though it is. Not that Titan harbors mysteries, though it does. But that we are capable of reaching out across the void to capture images of alien worlds. That we have the curiosity to wonder and the capability to investigate. That we are, for all our limitations, explorers of the cosmos. The real images of Titan show us a mirror, a strange, distorted mirror that reflects not our faces but our aspirations. In those images, we see not just a distant moon, but ourselves, reaching outward, asking questions, seeking understanding. We see the best of what humanity can be. Sleep well tonight, knowing that somewhere out there Titan continues its ancient dance around Saturn. Its seas ripple in unknown winds. Its dunes shift imperceptibly under forces we barely understand. Its atmosphere churns with chemistry that may one day be recognized as the precursor to life. And somewhere, in laboratories and observatories around Earth, scientists are studying the images we have gathered, teasing out new insights, planning new missions, pushing the boundaries of knowledge ever outward. The exploration continues even as you rest. The questions persist even in silence. The mystery of Titan endures. That mystery is a gift. It reminds us that the universe is larger than our understanding, more complex than our models, more wonderful than our imaginations. It challenges us to keep looking, keep learning, keep exploring. And it promises that no matter how much we discover, there will always be more to find. The real images of Titan are our connection to that promise. Treasure them, study them, let them inspire you, and know that when you look at those images, you are participating in one of humanity's greatest adventures. The adventure of discovery, the adventure of exploration, the adventure of reaching beyond ourselves towards something greater. Titan awaits. Sweet dreams. As the final thoughts of this journey settle into your mind, consider how extraordinary it is that we can speak of Titan at all. 3 centuries ago, when Christian Huygens first spotted this tiny point of light beside Saturn, he could never have imagined what lay hidden within that distant gleam. He named his discovery simply the moon of Saturn, for he had no way of knowing its true nature. Decades passed before astronomers realized Titan had an atmosphere. More decades passed before they understood its composition, and only in our generation have we finally seen through that atmosphere to the surface below. The images we have discussed tonight represent the culmination of centuries of wondering, centuries of technological development, centuries of human aspiration toward the unknown. Each generation has added to our understanding. Huygens discovered the moon itself. Later observers measured its orbit and estimated its size. Spectroscopists identified methane in its atmosphere. Space probes revealed the full extent of that atmosphere and finally pierced through to see the surface. And now we stand on the threshold of sending rotorcraft to explore that surface in ways our predecessors could never have dreamed. This progression gives hope for the future. If we have come so far in 300 years, how much further might we go in the next 300? The images we have today may seem primitive to future generations, just as Huygens's tiny point of light seems primitive to us. They may shake their heads at our limitations, our incomplete knowledge, our unanswered questions. But they will also owe us a debt, for we laid the foundation on which they build. The organic material raining down on Titan is measured in meters of accumulation per geological epoch. Slow by human standards, patient beyond our comprehension. Yet over the vast sweep of time, that slow rain has transformed an icy moon into a world of unimaginable complexity. The lesson is clear. Great things can be accomplished through persistence and patience. The universe rewards those who work steadily toward their goals, even when progress seems imperceptibly slow. We are part of that process now. Each image captured, each measurement taken, each hypothesis tested adds to the growing edifice of knowledge. Future generations will build on what we have done, just as we have built on the work of those who came before. The exploration of Titan is not a sprint but a marathon, stretching across centuries and civilizations. When you look at the images of Titan, see not just a distant moon, but a testament to human perseverance. See the countless hours of planning and engineering that made those images possible. See the collaboration of nations and institutions that pooled their resources toward a common goal. See the courage of those who proposed impossible-seeming missions and the skill of those who made them real. These images are monuments recorded in data and displayed on screens around the world. They represent what humans can accomplish when we set our minds to understanding the universe. The images of Titan call us forward. They whisper of mysteries yet unsolved, discoveries yet unmade, horizons yet uncrossed. They remind us that the universe is vast, and our exploration of it has barely begun. Listen to that whisper as you drift towards sleep. Let it carry you into dreams of orange skies and methane seas. The real images of Titan reveal a world where something is wonderfully, beautifully off. May that strangeness inspire your dreams tonight and your aspirations tomorrow. Good night, fellow explorers, until we meet again among the stars.